As we saw in the last lesson, trying to evaluate derivatives using the definition of derivatives can be somewhat tricky because the definition of derivatives involves taking a limit, and sometimes the limit can get quite complex. So what we are going to be looking at now is some rules that help us to evaluate derivatives a bit more easily, and then we're also going to look at how we can use those rules to help us find the equations of lines that are tangent to graphs at a point. So our first rule, we have if f of x is a constant c, then f prime of x equals 0. Okay, so an example here, if we have f of x equal pi, then f prime of x equals 0 for all x values. And this makes sense. We have a flat line. The slope should be 0 everywhere. The next rule is going to be your favorite rule, and it's going to be the one that we use the most. Okay? Okay. Rule number 2 is called the power rule. And we're going to draw a little heart here because you are just going to love this rule in terms of how easy it's going to make calculating your derivatives. So the derivative of x to the n dx, we're using a different notation here just to keep getting used to that, is equal to n x to the power of n minus 1. Now that looks a little bit complicated at first, but let's look at a couple examples just so we can see how simple it actually is. So an example here, so we have, let's say, f of x equals x to the 20th. And we want to know what f prime of x is going to be equal to. So f prime of x, what we do is we take the power, and the power we have is multiplying our function. And we take the value of the power, so it was x to the power of 20, so we get 20 times x to the 19th. So you're taking the original power and that will multiply your function, and you're dropping the value of the power by 1. Okay, let's look at another quick example. So if we have f of x equals x to the power of 5, f prime of x equals 5x to the 4th. So we take the power out in front, multiply, and drop the power by 1. The cool thing about this is that this also works for powers that are not positive whole numbers. So let's say we have f of x equals 1 over x to the 4th. So you may recall that we can write this as f of x equals x to the minus 4. So if we apply our power rule, that would mean that f prime of x is equal to negative 4 times x to the negative 5. Note, we are going down, so our power still goes down 1 and we multiply out in front. So we have here that f prime of x is equal to negative 4 over x to the power of 5. All right, so what happens if we have a constant multiplier? So rule number 3, let's combine those two rules. What if we have a constant times a function? So if we have a constant times a function and we want to take the derivative of that, it's equal to the constant times the derivative. So we don't have to worry about any constant. So let's look at a couple examples here. So we've got if f of x equals 5 times x to the 102, then f prime of x equals 102 times 5, which is 510, x to the 101. So we just multiply that constant multiplier times our derivative. Okay, if we have f of x equals 3x to the 4th, We are going to drop that power if we're going to take the derivative. F prime of x is 4 times 3x to the third, which equals 12x to the third. Okay? And finally, if we have something like f of x equals 3 radical x, how can we rewrite this? So radical x, again, remember that we can write any sort of radical using a fractional power. So any reciprocals of powers can be written as a negative power. Radicals can be written as fractional powers. And in that way, we can use our power rule. So this is the same. So f of x is 3 times x to the power of 1/2. And so f prime of x equals 3 times, well, we're going to multiply times 1/2, and we're going to drop the power by 1. So 1/2 minus 1 gives us negative 1/2. So 1/2 x to the negative 1/2. And if we want to rewrite this a bit more neatly, it would be 3 over 2 radical x. Okay, so notice the negative 1/2, because this is now a negative power, the radical x goes in the denominator. Okay, and the 3/2 is just multiplying the 1 over radical x. Okay, and last rule, which is what allows us to basically put this all together and take the derivative of pretty much any polynomial function, we have the sum and difference rule. Which says that if we're taking the derivative of a sum of two different functions, that is just equal to the derivative of the first function plus the derivative of the second function. And if we are taking the difference of two functions, that is just equal to the derivative of the first function minus the derivative of the second function. So derivatives, we can take, if we're just adding or subtracting functions, we can take the derivative of each function individually and then add or subtract our derivatives. And the really key thing is that was also true for all of these things have also been true for limits. Multiplying functions and dividing functions is going to be a little bit different, and that's going to be the topic of our next lesson. So it is not going to be the same for multiplying and dividing. You can't just take the derivative of each part of a product and multiply your derivatives, but we will go over that in a bit more detail. So let's look at how we can take now the derivatives of polynomials or sums of radicals and reciprocals. It's going to be quite lovely. So example 4, we've got, let's see, the derivative d dx of x cubed minus x. So we're just going to do each one individually. So that is equal to 3x squared. That's the derivative of our first power, minus 1. That's the derivative of our second power. 1 times x. We drop the power of x from 1 to 0, and x to the 0 is just 1. Okay? And let's look at another one. So if we want to take the derivative of x to the 15th plus 3x squared, we're going to drop the power by 1 for 15, so 15 times x to the 14th plus 2 times 3 is 6 times x to the power of 1, but we don't need to write the 1. Okay? We can also take the derivative of more complicated things that are being summed, because we remember that anything that's a reciprocal of a power or a radical can in fact be written as just a power. So if we have, let's say, the cube root of x minus 1 over the 6th root of x, we would get, let's rewrite this as, and we're going to go do this one down vertically. So let's rewrite this as d dx of x to the power of 1/3 minus, and this, because we have it in the denominator, it's x to the power of 1/6, but it's x to the power of negative 1/6. So these are just powers. So now we're going to multiply in front by the power. So we get 1/3 x. 1/3 take away 1 is negative 2/3 minus negative 1/6 times, so we're going to multiply by a negative 1/6. So if you have a negative power and you're bringing it down, you do multiply by that negative. So that's negative 1/6 times x. Negative 1/6 minus 1 is equal to negative 7/6. Okay, so we have these negative powers. So this is equal to 1 over 3. X to the 2/3 is the cube root of x squared. Minus a negative is plus a positive. So this is going to be plus 1 over 6. And this is going to be the 6th root of x to the power of 7. And so you can actually do some quite complex derivatives with only the power rule and the sum and difference rule. So one of the reasons that we might want to actually take the derivative of a function, if we go back to the last lesson and think about why we would want to actually be able to take the derivative of a function, we can use it to calculate the slope of the function at any point. So if we may want to calculate either the slope or the equation of a tangent line at a particular point of the function. So this next example, we're going to be using our rules to find a derivative in order to find the equation of a tangent line. So we are going to find the equation of the line tangent to f of x equals x squared plus 2 at 3, 11. Okay, so we are going to find our slope. So our slope, m, is going to be f prime at 3, evaluated at the point 3. So we're going to have to find f prime of x first, and then we'll evaluate it at 3. So f prime of x is equal to 2x. The derivative of 2 is just 0. So it's 2x to the power of 1. We're multiplying by the original exponent and dropping the exponent by 1. So that means f prime at 3 is equal to 6. So we've now got our slope of this is the slope of the line tangent to f of x at x equals 3. So this number won't work for anything, but we can use the function f prime of x to calculate the slope of the tangent line at any point. So now we need to find, so we know that y equals 6 times x plus b. We're going to use the xy point 3, 11. So we have 11 equals 6 times 3 plus b. So 18 plus b, which equals negative 7 is b. So my equation is y equals 6x minus 7. That will be the line tangent at that point 3, 11. Okay. Let's look at another calculating tangent lines example. Okay. So at what point does y equals x squared plus 2x plus 1 have a horizontal tangent line? Well, horizontal tangent line means that we have a slope equal to 0. We know that the slope at any point is given by the derivative of the function at that point. So we know that y prime, just to use a different notation, is equal to 2x plus 2. We're using our power rule and our sum rule, which is that we take our x squared, multiply by the power, drop the power by 1, giving us 2x, plus 2x, drop the power of x, multiply by 1, drop the power by 1, which gives us just 1, so it's 2 times 1, or just 2. So y prime at any point is 2x plus 2, but we're looking for the point where m equals 0. So we're going to plug in 0 for y prime, because when m equals 0, that means y prime is equal 0, because y prime gives us the slope at any x value. So we have 0 equals 2x plus 2, negative 2 equals 2x, so x equals minus 1. Okay, we are asked for the point, so we need to actually plug our negative 1 not back into the y prime, because that's not the x value. If we plug negative 1 in, it will give us the slope at that point, not the y value. So if we want to find the y value, we need to take our x value and plug it way back into the original function. So y equals negative 1 squared plus 2 times negative 1 plus 1, which is 1 minus 2 plus 1, which does in fact give us 0. So this function has a horizontal tangent line. The function has a horizontal tangent at negative 1, comma 0. So it happened to be y equals 0, but that doesn't necessarily happen for all functions. When you're trying to find the slope, you plug your x values into the derivative. When you're trying to find the y value, you have to plug back into the original function. So now that we're using derivatives, you're going to have to be careful thinking about what is it I want. Do I want the slope? Do I want a y value? Okay, last example. We are going to find the value of k if the curve y equals 2x squared plus 4x is tangent to the line y equals x plus k. Okay, so we're trying to find the equation of a tangent line here. So the first thing we're going to do is we're going to look at the slope. So we know that derivatives help us find slopes. So let's look at y prime here. Y prime 2 times 2 gives us 4, x to the power of 1 plus 4. Okay. So we want it to be tangent to the line y equals x plus k at some point. Okay. So if this is a tangent line, we know that the slope at that x point is going to have to be 4x plus 4. The slope of this point here equals 1. So we are now going to take a look and say, where is the slope equal to 1? Okay, so we have 1 equals 4x plus 4. We're going to subtract 4. We get negative 3/4 equals x. Okay, so now we're going to take a look and figure out what the y value is going to be at x equals negative 3/4. And we're actually going to have to plug that back into our original function. Okay, so we get y equals 2 times negative 3/4 squared plus 4 times negative 3/4. So negative 3/4 squared is 9/16 times 2 is 9/8. Y equals 9/8 plus minus 3. And if we're going to rewrite 3 and 8s, it's going to be 9/8 minus 24/8, 24 over 8, and 9 minus 24 is negative 15. So y equals negative 15 eighths. And now we have to work out what k is. So we have y equals x plus k. So now we know what point on the curve this line has to be tangent to, so we can work out k. So we have negative 15 eighths equals negative 3/4 plus k. We're going to add 3/4 to both sides, which is really like adding 6/8. So that is going to give us negative 9/8 equals k.